Hello, you are welcome to the Phases for Senior High School. Today, we are looking at dimensional analysis, one of the foundational topics for first year phases. For our lesson objectives, this lesson will seek to look at a detailed definition of dimensional analysis and other related terms that goes with it. We also go into derivation of dimensional equations for certain quantities. And for this, our first lesson, we'll look at area and volume. The rest will follow in subsequent videos. So, as a way of going by the objectives, the first is what is the definition for dimensional analysis? And it is a process of converting a physical quantity from its derived unit into its fundamental unit. Basically, dimensional analysis looks at a derived unit and out of it break it down to its fundamental unit. So that process of achieving this is what is called dimensional analysis. Example, let's have a derived unit called Newton, the unit of force. Now, if you look at force, force is mass times acceleration. And so the derived unit of Newton simply could be breaking down as kilogram meter per second square, where the kilogram means mass, the meters per second square is acceleration. So that process of breaking down a derived unit into its fundamental unit is dimensional analysis as earlier defined. Let's look at some related terms that are essential for us to know as long as dimensional analysis is concerned. The first is dimension of a physical quantity. And this is simply the algebraic symbol that is assigned to the individual physical quantities of a dimensional equation. So the dimensions simply are the symbols we assign the various quantities in an equation that is dimensional. And to write it, dimension of physical quantities are always written in square brackets, as you can rightly see here. That's if we want to say the dimension of length is written as length in a square bracket. The same applies to dimension of mass. This is how it's written. And so if you see it written this way, it is read as dimension of the quantity expressed in it. The second related term is dimensional equation. And this equation only expresses the physical quantity in terms of a dimension. So any equation that tells a physical quantity in a dimension is a dimensional equation. And it can also be a representation of a derived unit as a product of its fundamental unit raised to some power. To break this one down, we used Newton earlier. So Newton is the derived unit and it comprises of kilogram, meters, second, and to the power negative 2. So a representation of this derived unit Newton as a product of its fundamental unit, that is kilogram mass seconds, raised to some powers, is what we refer to as dimensional equation. And so this is how it is. In order to write the equation, you then convert the kilogram to its fundamental unit, which is mass, the meter is the fundamental unit for length. The second is for time. And so dimensional equations are written as this: MLT negative 1 for Newton. We'll look at other interesting ones before the lesson ends. The third related terms that should be known is dimensional constant. Basically, these are constants that have dimensions. Example, we have Planck's constant H, it has dimension. Universal gravitational constant G, the Coulomb's electrostatic constant K, the Stefan Boltzmann constant. So all of these, though constants, they have dimensions, and you will see all of this in subsequent videos. The fourth related term is dimensionless constant. So just as we just defined for the third one that dimensions with constant are dimensional constant, constant that do not also have dimensions are called dimensionless constant. An example is one numbers: 1, 2, 3, half, 1/3, root 2, both rational and irrational numbers. These are constants, but they do not have dimensions. So keep this thing very important. If in an equation, in an expression, in a deduction, if you have numbers expressed, while you are trying to convert them to their fundamental unit, numbers do not have dimensions, and so they are ignored. We also have constants such as pi, which you can also call the Archimedes constant, as well as the natural logarithm, which you can also call Euler's number. These do not have constants, and so they are dimensionless. Or these constants don't have dimensions, and so they are dimensionless. The last example is when you have trigonometric functions such as sine, cos, and tan of a certain angle. These functions do not have dimensions, though constant. Okay, still another fourth. Let's know this. Dimensionless constants are ignored in dimensional equation. I earlier said this. So in an equation, you ignore them. Example, you are given E equals half mv squared. That is kinetic energy. Now, while converting this to the dimensional equation, the mass and velocity could be expressed, but the half is a number, and so it is ignored in the conversion from the derived unit to the fundamental unit. Another example is area of a cone, 1/3 pi r square h. The pi as well as the 1/3 are all dimensionless constants, and so the focus will be on the radius square and the height. Last one, this is what we call the time of light. I know this is an early physics for you. You will see all these things by the end of your study with physics for the period that you are supposed to be in school. This is 2u sine theta over g. Looking at this, as we earlier said, the 2 is a number, and so it doesn't have a unit. This is u. It stands for initial velocity, and so it can be converted. Sine theta is a trig function, and it does not have a dimension. G is acceleration due to gravity, and it has a dimension. So now here the focus will be on the u and the g, since the u and the sine theta are dimensionless. Thank you very much for your audience. Now we'll look at the various dimensions, and they are assigned units and symbols. So as rightly said from the beginning, dimensions of physical quantities are written in square bracket. And so this is read as dimension of mass. The unit of mass is kilogram. expressed as kg. In writing its fundamental unit out of the derived unit, it is symbolized with capital M. Length. Length has got the unit meter, written as small m. Its fundamental symbol is L, capital L. Time, with a unit of seconds, S. Its symbol for the fundamental unit is capital T. Electric current, ampere. The symbol is also A. Temperature, Kelvin, but the symbol is a theta. Amount of substance, the unit is mole. The symbol is a capital N. Luminous intensity, candela. The unit is CD, but the symbol is a capital G. So these are the known 7 fundamental quantities. They are units and they are symbol. I trust that you have remembered all this. Okay, friends, let's take note of this important point, especially for length. These quantities, distance, displacement, width, breadth, height, radius, diameter, base length, length of an arc. All these are one thing. Any of these could be converted into the symbol or unit as meter because they have their dimension as length. So keep this in mind. Length expressed in different ways. So this is an important point to note. Great. And so let's look at some various dimensional equations of some selected physical quantities, which we know will be the basis for all discussion. Now, these are the quantities and their dimensional equation. Area. Area has the dimensional equation as L square. Volume, L cube. Mass density, ml exponent negative 3. Area density, ml negative 2, and so on and so forth. Now, our task is, as way of our objectives, we will be looking at just this first two, why their dimensions are expressed as they have been specified. By the end of this subsequent lessons, the dimension analysis, we will derive all these dimensional equations. So stay tuned as I switch over from the presentation board to the writing board. Thank you very much. So hello friends, welcome to the writing board where I can write visibly for you to see. We earlier looked at some various dimensional equations. Then for our objectives for today's lesson, we'll look at just area and volume. Let's start with area. The dimensional expression or equation for area was L exponent 2. But take note, there are many areas of plane figures and even solid figures. So do all of them have their dimension equation to be L to the power 2? Yes. Let's prove it. Let's start from area of a rectangle. Mathematically, the area of a rectangle is expressed as length times breadth. So that is the formula. If that is true, then we need to convert each of them into their dimensional form. Now take note that length has got the dimensional or the dimension to be L times breadth. We said breadth also has got the dimension to be L. Now L times L is equal to L squared by the rules of indices. Since the bases are equal, the exponents are all 1 and 1. Therefore, as the base multiplies, the exponents are added, and that is why it is L squared. So that is it. Area has L squared. Let's try another shape, and that is area of a triangle. Mathematically, the area of a rectangle is written as half of the base times the height, the triangle. Great. We need then convert these expressions to their dimensions. For half, it has been established earlier that it is a dimensionless constant, and so it has no dimension and it is ignored. The next is the base length. Base length has got its dimension unit to be length, that's the symbol we subscribe to, times height also expresses a length, and so its symbol in dimensionally is also L. The L by L is equal to L squared. So the area of a triangle also follows the same as that. Again, the area of a sphere. Mathematically, the area of a sphere is 4 pi r squared. Great. With this, we have to express each quantity in their symbol as dimensional equation. 4. 4 is a number, and numbers are dimensionless, hence ignored. Pi. Pi, Archimedes' number, is also dimensionless, as earlier stated. Radius. Radius is expressed as length, and so it has its symbol to be L, and it's also squared, so you add the square to it. So friends, have you noticed that that's also L squared? Let's continue with surface area of a solid cylinder. It's an area, right? And mathematically, that is also expressed as the summation of the cross-sectional area. One is pi r squared, and so two of them become 2 pi r squared. So let's take a cylinder to be a tin of milk, new one. So the circular edges, when added, you have 2 pi r squared plus the curved surface area, where there is the paper label. It's written as 2 pi RH, the curved surface area. Now, it is our task to express this as dimensional equation. And so, we start by looking at each individual term. 2. 2 is dimensionless constant, so ignored. Pi, dimensionless constant, so ignored. Radius is a length, and it is squared. Plus 2, ignored because it is dimensionless. Pi, ignored because it is dimensionless. Radius has its unit to be length times height, also length. So bringing the two of them together, I will have length square plus length times length also gives you length square. L square plus L square will amount to 2L square. Finally, remember that 2 is still a dimensionless constant. And so when the 2 is ignored, we are left with L squared. So I think up to this far, so long as it is an area, it has a dimensional form, a dimensional unit, a dimensional equation to be L exponent 2. I believe you have understood this very well. On your own, you could consider other shapes like the cone, like the other shapes which you can recall in mathematics. Thank you very much. Let's now look at volume. Volume has a dimensional equation as L exponent 3. Let's look at some various shapes that has volume. Volume of a keyboard. Mathematically, the volume of a keyboard is written as the length times the breadth times the height. That is it. Friends, now expressing this in the dimensional form, length has got 8 units as L. Breadth has got the unit as L. And height also as L because they all express length. Per the rules of indices, when you have common basis multiplying, one of them is written, then by virtue of the multiplication, the exponents are added. So 1 plus 1 plus 1 is equal to 3. And that gives L cube. Same as this. Again, volume of a cylinder. The volume of a cylinder is pi r square h. Expressing this in dimensional form, pi is dimensionless, hence ignored. Radius has got the symbol to be length. Then it is squared times that of height is also length, L. So L square times L. The exponents are added as earlier explained. So that also gives you L exponent 3. Again, the volume of a cone is synonymous to that of the cylinder. That is only 1/3 pi r square h. With this as well, 1/3 is a number and hence ignored. Pi is a number and hence ignored because it's dimensionless. The radius has a dimension to be square of L, that's L square, times that of the h as L. Together, you get L exponent 3. Lastly, let's look at the volume of a sphere. It is expressed as 4 over 3 pi r cubed. With this, the 4 over 3 is a number, hence ignored. The pi is a constant, a dimensionless constant, hence ignored. The r has got its unit as L and also to the power 3. So friends, that is to say, whichever volume you know of any shape has still got its dimensional equation to be L exponent 3. So that is the end of our lesson for today. And that is the objective we set for ourselves for today. Thank you very much. Take a break and continue the other lesson. It promises to be very, very interesting. Thank you for your audience and be blessed.